Have you ever wondered about the mysteries of plutonium, an element so powerful yet so dangerous? Plutonium, denoted by the symbol Pu, holds the 94th position on the periodic table. Unlike elements found in nature, plutonium is transuranic and synthetic, meaning it doesn't occur naturally in significant quantities. It's birthed in the heart of nuclear reactors, where uranium-238 is bombarded and undergoes a series of nuclear reactions, giving rise to various isotopes of plutonium. Among these isotopes, plutonium-239 and plutonium-240 are the most significant. Plutonium-239, with its ability to sustain a nuclear chain reaction, is invaluable for nuclear weapons and fuel in certain nuclear reactors. Plutonium-240, however, presents a challenge due to its high rate of spontaneous fission, leading to complications in both nuclear weaponry and reactor operation. So, plutonium, a key player in nuclear weapons production, is a force to be reckoned with. But it's not just its strength that's intriguing, it's the dangers and challenges it poses. Stay tuned as we delve into the discovery of this fascinating element. The birth of plutonium dates back to the 1940s. When the world was caught up in the throes of the Second World War, a team of scientists at the University of California, Berkeley, led by Glenn T. Seaborg, made a discovery that would change the course of history. They created a new element, plutonium, by bombarding uranium-238 with deuterons in a cyclotron. The creation of plutonium is an intriguing process, one that takes place in nuclear reactors. Uranium-238, a naturally occurring isotope of uranium, is irradiated or exposed to neutron radiation. This bombardment transforms uranium-238 into plutonium-239, a new isotope through a series of nuclear reactions. But plutonium-239 is not the only isotope of plutonium. Plutonium-240 is another significant isotope, albeit a byproduct of the nuclear reactions that create plutonium-239. It's known for its high rate of spontaneous fission, which poses its own set of challenges, from pre-detonation risks in nuclear weapons to complications in reactor operation. These two isotopes, plutonium-239 and plutonium-240, are the most common and significant forms of plutonium. They contribute to both the potential and the challenges of this element, from its role in nuclear weapons and reactors to the issues around its handling and disposal. So, the birth of plutonium marked a significant milestone in the field of nuclear science. Plutonium, like a coin, has two faces, one destructive, the other constructive. This heavy, radioactive metal bears an uncanny resemblance to the mythical god Janus, the two-faced deity of transitions and duality. With its atomic number of 94 and the symbol Pu, plutonium sits heavy on the periodic table, a testament to its weighty implications. On one side of the coin we have plutonium-239, the fissile isotope. This is the stuff of nightmares and apocalyptic visions, the core component of nuclear weapons. It's the element that makes the mushroom clouds, the one that can sustain a nuclear chain reaction and release an immense amount of energy in a split second. It's the stuff that powered the Fat Man bomb dropped on Nagasaki in World War II, a deadly demonstration of its destructive power. But let's flip the coin. We land on plutonium-240, another significant isotope, yet a byproduct of nuclear reactions. It's this isotope that contributes to the challenges of handling and disposing of plutonium due to its high rate of spontaneous fission. However, it's not all doom and gloom. Plutonium-239, the same isotope that can cause so much destruction, also has the potential for constructive use. Here's where the other face of plutonium shines. It's not just a weapon of mass destruction, it's also a potential source of mass energy production. Plutonium-239 can be used as fuel in certain types of nuclear reactors, such as breeder reactors. These reactors have the unique ability to produce more fissile material than they consume, making plutonium a valuable resource for sustainable energy production. This dual nature of plutonium, its ability to both destroy and energize, is what makes it such a fascinating and controversial element. It's a testament to the power of nuclear science, a demonstration of how we can harness the forces that bind the universe together, for better or worse. Indeed, plutonium's dual nature makes it both a blessing and a curse. It's up to us to decide which face we choose to see and how we use this incredible, potent element. Handling plutonium is no child's play. It's a task fraught with danger and challenges. This heavy metal with the atomic number 94 is a synthetic element that doesn't occur naturally in significant quantities. But don't let its scarcity fool you. As a transuranic element, plutonium possesses properties that make it both a boon and a bane. The most common isotopes of plutonium are plutonium-239 and plutonium-240. While the former is fissile and can sustain a nuclear chain reaction, the latter is a byproduct of nuclear reactions. Plutonium-240 has a high rate of spontaneous fission, a trait that contributes to the challenges of handling and disposing of plutonium. Imagine being tasked with handling a material that, if mishandled, can lead to pre-detonation in nuclear weapons and cause complications in reactor operation. It's akin to walking on a tightrope over a sea of potential chaos, but the challenges don't stop there. Storing plutonium is equally daunting. It's not something you can just wrap up and stash in the corner of some warehouse. Plutonium is radioactive and toxic, posing significant health and environmental risks. Proper storage methods are crucial to prevent leakage and contamination. Disposing of plutonium is yet another hurdle. Given its long half-life, the disposal of plutonium is a problem that spans millennia. It's a ticking time bomb that we pass on to future generations unless we find a way to neutralize it or put it to good use. Beyond these physical challenges, there's also the specter of nuclear proliferation. Plutonium can be used to produce nuclear weapons, and if it falls into the wrong hands, the consequences could be catastrophic. The world needs to remain vigilant and adopt stringent measures to prevent misuse. So, as you can see, the handling of plutonium is a matter of great concern and requires utmost caution. The story of plutonium is a tale of scientific marvel and cautionary tales, a testament to human ingenuity and the challenges it can pose. The question remains, how do we secure the future with such a potent element in existence? A crucial query that necessitates a comprehensive answer. For starters, the handling of plutonium is not a task taken lightly. Stringent regulations are in place, and the element is managed with utmost care to ensure its safe storage and disposal. But the challenge doesn't end there. The nature of this element, potent enough to fuel both destruction and progress, demands international cooperation. We live in a world where the misuse of plutonium could spell catastrophe. Hence, a collective effort is vital to prevent such a scenario. This is where international agreements and safeguards come into play. Countries across the globe have come together to form pacts and policies aiming at the secure management of plutonium. These agreements enforce the responsible handling of this element, stipulating conditions for its use, storage, and disposal. There's a common understanding that the misuse of plutonium is not just a threat to one, but all nations. In addition, there are ongoing efforts to enhance the safety measures in place. These include the development of advanced storage facilities and improved disposal techniques. The aim is not just to contain plutonium, but to manage it in a way that minimizes the risk it poses. The future of plutonium thus lies in our hands. It's a responsibility we all share to ensure that this potent element is a tool for progress, not destruction. As we near the end of our journey, let's summarize what we've learned about plutonium. Our story began with the birth of this new element, a transuranic entity with an atomic number of 94. A synthetic creation, plutonium doesn't occur naturally in significant quantities, but rather, it's primarily produced in nuclear reactors by irradiating uranium-238. We've delved into the dual face of plutonium. On one hand, we have plutonium-239, a fissile isotope that can sustain a nuclear chain reaction. This makes it a valuable resource for nuclear weapons and a potential fuel for certain types of nuclear reactors. But then there's its sibling, plutonium-240. This isotope serves as a byproduct of nuclear reactions and poses a challenge due to its high rate of spontaneous fission. This property can lead to complications in reactor operation and even pre-detonation in nuclear weapons. But like most things in life, plutonium is not just black and white. It has the potential for both creation and destruction. It's a key material in nuclear weapons production, being used in both fission and fusion weapons. At the same time, it harbors potential for peaceful applications, primarily as a fuel source in certain types of nuclear reactors, like breeder reactors, which produce more fissile material than they consume. Yet we can't ignore the challenges that come with handling plutonium. Its radioactive and toxic nature makes storage and disposal a significant issue. The potential for nuclear proliferation is a grave concern, as plutonium can be weaponized if it falls into the wrong hands. Thankfully, efforts to secure and manage plutonium stockpiles are ongoing, with international agreements and safeguards in place to prevent misuse. And there you have it, the enigma of plutonium unraveled. Join us next time as we uncover more mysteries of the universe.